This is lesson 23 of the Quantum Mechanics, a mini lecture series titled De Broglie's Confirmation of Bohr's Fourth Postulate. So de Broglie did something really amazing, among other things, among his work on the wave-particle duality. Something that really fascinates me every time I teach this to my students. It's still the same thrill that I get. It's just absolutely amazing. So de Broglie basically took a wave and he decided to wrap it around in a nucleus. Let's take a hydrogen atom. Wrap it around a nucleus as follows to explain the stability of an atom. Okay, so an electron moves around in an atom with its associated wave being stationary, okay, in a standing wave pattern. What's a standing wave? Suppose you get a wave, fix it between 2 points. This is called and you vibrate it. Okay, you pull one part of it up and it'll start to vibrate like so. You'll get a standing wave. Standing because it's just standing, it's doing nothing. It's just sitting there. You'll get nodes. A node is a point on the wave where the wave isn't moving. So the two fixed points, they're nodes. Where the wave is oscillating, place where the wave is oscillating, that's called an antinode. Okay, it's the maximum amplitude, if you wish. Just like a wave moving along a guitar string, okay, because the guitar string is fixed at both ends. So then, therefore, only discrete frequencies are produced. You only get very specific frequencies. So in other words, n lambda is equal to 2 pi r. This was de Broglie's condition. You can only fit a whole number, n is an integer, whole number. Okay, it could be 1, 2, ... 2 pi r, that's the circumference of a circle. If you recall back to junior maths, circumference is 2 pi r, r is the radius of the circle. So let's draw this standing wave again. Okay, here's the nucleus, distance r. Wave is distance r away from the nucleus. You can't have this condition where the wave doesn't come back on itself. So if I draw this, let's say, that is not a standing wave. Okay, this condition isn't satisfied, not equal to. That's what this symbol here means. So only a certain whole number of wavelengths will fit around a circle. So remember, Bohr needed to actually account for the unexplained 2 pi factor in his fourth postulate, okay? Quantization of angular momentum. Okay, if you recall, angular momentum in physics is given the symbol L. That's mvr. Okay, momentum times r, radius, because of circular motion. It's n h over 2 pi. Okay, h over 2 pi, that came from a paper written by John Nicholson, a physicist, on atomic theory. Okay, now the 2 pi can be accounted for in terms of a circle. So here's the magic that de Broglie developed, n lambda. So we started off with this. Okay, this is called the standing wave relation, standing waves relation. Okay, this is how you get standing waves in an atom. If you plug in lambda for h over mv, remember this is de Broglie's wave-particle duality. Lambda is h over mv. This is using the de Broglie relation. And you rearrange, what you'll find, so nh over mv is 2 pi r. Let's rewrite this as nh. So let's swap, mathematically you can do this, let's swap the 2 pi with the mv. So you get 2 pi mvr, which is just Bohr's fourth postulate of the quantization of angular momentum. Absolute magic. So now Bohr's postulate is a fact, it's a reality. Okay, electrons are really just waves, standing waves around a nucleus.